Okay, so I'm going to teach you today about that pesky ambiguous case that I mentioned yesterday. So here we go. Okay, I would like for you to copy down this diagram, the same diagram 3 times. So notice that this is an angle of 30 degrees. Yours doesn't have to be exactly 30, but approximate it. But I would like you to make this other arm from A to C to be exactly 5. So if you wouldn't mind, copy that diagram once and then maybe trace it twice more just so you have 3 that are exactly the same on your paper. So please pause this video and everybody take a sec to copy this down thrice. Okay, so hopefully you've all had a chance to do that now. So you'll notice that there are instructions for each one. First one asks us to put a point B on the lighter gray line such that from C to B is 2.5 centimeters. So I want you to actually measure it out. There are some rulers in the cupboard at the front of the room if you want to pause this video and go grab those rulers. Okay, so this line is going to go from C to this gray line, a point on that line which we're going to call B, and we want that line to be 2.5 centimeters. So take a sec right now, take this point, connect it to the gray line, but make sure that the line that you create is only 2.5 centimeters long. So wherever it lands on here, on this gray line, but so that's 2.5 centimeters. On this one, you're going to do the exact same thing. So you're going to connect this point C to this gray line down here. But the line that you use to connect C and the gray line is going to be 6 centimeters long. So again, you're going to measure it out. And then again, you're going to ask how many options you have on the placement of B. So could you put that point B in 2 different places or 3 different places or 4 different places? How many different places could you put B that would make it work? Okay, so that would put that point somewhere on this gray line. And then lastly, you're going to do the third example, where again, you're going to put a point B somewhere on this gray line, but the line that you're going to create that connects the line here to C is going to be 3.5 centimeters. And again, you're going to wonder, how many options do I have? So I'm going to try to come up with as many different places that you can put B. So again, please pause the video and everybody take a few minutes just to do that. And you can talk to each other about it. Make sure you are measuring. Each line should be 2.5 here, 6 here, and 3.5 centimeters here. How many triangles can you create? So please stop the video and do that. Okay, so now that you've all had a chance to do that, hopefully you have found that the ambiguous case exists. So some of you might not have jumped out just yet. So okay, so let's say you have this scenario right here, and hopefully you found that there's actually only one place where you can connect this point, C, to this gray line in order to make that 2.5 centimeters. So that's kind of, I chose that on purpose so it would work out. So this is 2.5 centimeters, and it connects only once. Okay, so that's a length of 2.5 centimeters. So that length creates only one possible triangle. There's no question about it. You can't make a line that's the same length. Let's say that it's the same length like this one. Okay, that these 2 lines are the same length. Notice that if I try to put it over here, I can't. It's too short. It doesn't quite reach that gray line. Same thing here. If I take the line that's the same length, again, it's way too short. It doesn't fit that gray line. It's not going to make it over here without changing the length, okay, without making it greater than 2.5 centimeters. Down here, you had a little more room to play with. You had a line that was supposed to be 6 centimeters, so that was quite long. So your first one might have ended up like, say, over here. Okay, so that would create a triangle. Mine's kind of rounded, but you kind of get the idea. So that would create one possible triangle. The other option that you might have done is you might have tried to do a line going this way, and that was also 6 centimeters. So if this was 6 centimeters and this one was 6 centimeters, and if it reached the gray line as though it were to continue that way. Okay, so maybe you did that, maybe you're thinking outside the box, and that's really cool. The only thing is that if you did that, you ignored this 30-degree angle. Okay, so what we're talking about is if we're given a triangle that has these 3 things, it has, we're given 2 side measurements and an angle measurement. So this 30 was, say, part of those given measurements that you were told, okay? So we can't just pretend that that 30 is not there, because that was what the question said. It said we have a triangle that has an angle that's 30 degrees, so this one over here, even though it's creative, it is not valid. Sorry. Okay, then there's this one down here, and this time you were supposed to create a line that was 3.5 centimeters, so that one is sort of like Goldilocks, if you see what I mean. Hopefully you'll see what I mean in a sec. Okay, so 3.5 centimeters is just long enough that you can create a triangle that's, say, going this way, which is nice and pretty. Just like this one, nice pretty triangle worked out. But what's interesting is that if you take the same length, so if this is 3.5 centimeters, if you take a line that's the same length and you put it the other way, you can still join, so assuming that this length and this length are the same, okay? You can still join that point C to this gray line at B, but that point B could be over here, or that point B could be over here. And what's weird is that both of those triangles are totally valid. Okay, we have a triangle that happens here, and we have a triangle that happens here, and both of them have the same sort of given measurement. So they both have a side length of 5, another side length of 3.5, and an angle of 30 degrees. Okay, if you agree, you see those two scenarios. You have this outer triangle. Let's maybe change the color here. Magenta. Okay, so we have this outer triangle like that, and then we also have maybe green. This inner triangle like that. Okay, so two different triangles, but both of them have all of these three things. They have two side measurements of 5 and 3.5, and one angle of 30. Weird. Okay, so that's why it's called the ambiguous case, because it's ambiguous. If you're given a question like this, you have to wonder, okay, well, which triangle was the one that I was supposed to get? Okay, so it's ambiguous. It wasn't specified. Okay, so that is the whole thing about the ambiguous case. So you're given A, B, and A, meaning two sides, and the angle that's across from one of those sides. So this is a fixed length that you're given, and you're not really sure where it needs to go, okay, in order to create this angle and to maintain this fixed length as well. So it's called the ambiguous case because that's what the word ambiguous means. It means open to two or more interpretations. So if you're given two angles on one side, then the sine law nicely provides you with one solution. So this is the scenario where you don't have to worry about the ambiguous case. But it does have an issue dealing with that SSA, that pesky SSA that if you read backwards would remind you that this is the one that is going to cause you some pain. Okay, so whenever you have those two measurements that are next to each other and an angle that's not between them, you could have the ambiguous case. Okay, so we're just going to break from here for a second. I'm going to show you in animation because PowerPoint's not that great. Okay, so again, it's kind of like if I am given some parameters. I'm given this angle of 30 degrees, and I'm given this length of 20. Okay, so those two are going to stay the same. But this length right here, little a, okay, is maybe going to change. So right now it's some length, which right now is at 10, actually. And if I increase the length of that line, then I have lots of possibilities, each of these lengths. So notice that this is 12.4, this is also 12.4. So those are the same length. And that creates two triangles. I have this triangle here, and then I'll have the bigger triangle on the outside. So there are lots of different values for that length. A could be all these different lengths. Could be 16.3, could be 17.1, could be 17.6, lots of different measurements, and all of them create these ambiguous triangles where we're not really sure which one we're talking about, okay? So which one is the question asking us to deal with? So it's ambiguous. What happens now if I make that too long? So you'll notice it's sort of like approaching some kind of space and you're not sure what's going to happen. If you go a little further, then it stops having multiple options, okay? So there is no other scenario. This line is too long. It's 29.8 or 28.4, let's say. It's too long for it to show up on the other side. So if I tried to make it go this way, it would no longer have that angle of 30 degrees. Uh-oh, I can't get that slider back. Oh no. Okay. Oh, I can move that. That's neat. Okay, so if I continue to make my other length smaller, so here's that nice scenario where I have, oh nice, I only have only one and it's short, or you can have only one and it's long. But it gets to a place when it's actually too short. And then there's nothing you can do to this side here that's going to make that reach this here, okay? And this side isn't going to move because you have this fixed angle, okay? This is 30 degrees, so I can't bring this one closer without changing that 30 degrees. So it can happen where that A gets too small and then you actually have no solutions. So you can have no solutions, you could have exactly one solution, you can have exactly one solution this way as well, or what's almost more common is to have two solutions, which is what happens when you have all these different measurements. All of these provide us with two different triangles that it could be. Weird. Okay, let's go back here. Okay, so here's some examples. So in triangle ABC, A is going to be 20, and C is going to be 16, and then angle A is going to be 30. We're going to stick with that nice pretty 30. The question is, how many distinct triangles can be drawn given these measurements? So now that you understand what the ambiguous case is all about, now we're going to be able to use what we learned in the last unit, so you don't have to think so hard every time that you deal with this. Okay, we're going to use, I'll tell you right now, we're going to use this cast rule, so you'll see how in a sec. Okay, so how many distinct triangles can be drawn given these measurements? So what we're going to do is we're going to use sine law, because we're going to try to figure out, well, right now we have what we talked about yesterday. We have this angle, and we have its opposite side. Okay, so right now we have what we called yesterday the glasses. That pen color is kind of weird. Okay, so we have this angle right here, we have its opposite side, we have glasses, which means that we can use sine law. And we can use sine law specifically since we have side C. Right now we can make another set of glasses if we attempt to find angle C. Okay, so that's what we're going to do. So let's try to find out what angle C would be, and we'll see if we get different answers or what. Okay, so I'll start down here. Okay, so we're going to use sine law to find C, which refers to angle C. And because I'm looking for an angle C, I'm going to do sine of C on top, and then little c is going to go on the bottom. And we know that little c is 16, so I write 16. And that's going to be equal to sine of A, which in our case is 30, over little a, which in our case is 20. Okay, so now we're just going to use sine law like normally. So again, we're looking to isolate C. So what do we have to do to isolate C? Well, we have to get rid of the 16. So we can do that by multiplying by 16 on both sides to make it even. And so that leaves us on this side now with just, oh, that's too dark. Sorry, too light. Okay, so there's sine C equals, on the other side now we have 16 times sine of 30 over 20. All right, and now we almost have C by itself. How do we get rid of the sine? Right, we do sine inverse. So now we have sine inverse of this whole thing. And that whole thing is, I'm going to just approximate it or calculate it and just tell you that it is 0.4 right now. Okay, so now you do sine inverse of 0.4 and you find out that C is 24 degrees. Awesome. Woohoo. That's just dandy. C is 24. And that's a final answer, so I'm going to box it. Okay, and that seems like pretty reasonable. This seems like it could be 24, so that's probably what our answer is going to be, but like, hey, you never know. There could be another one. So we have to check. And this is how we check. So we know that we took sine inverse of 0.4, meaning that we knew that sine C was going to be positive. So that means that this thing right here was equal to 0.4. Okay, so here it says sine C equals 0.4. We did sine inverse to find 24. Okay, because this thing, when you multiply it out and divide by 20, you get 0.4. Okay, but we know from last unit that sine is positive in two places. This is your Cartesian plane. Sine is positive in this quadrant and positive in this quadrant because of the cast rule. So our angle could be 24 degrees Or it could be in this quadrant as well. We're not sure. Where this related acute would be 24, which means that our other possible angle